Okay, next talk today is John Sous that will speak about Fracton conservation law in whole doped antiferromagnets. Please.
Thank you. So I would like first to thank the organizers, Andrea especially, for organizing that meeting and allowing people to come in person during these unusual times. So today I want to tell you about work I've done with Michael Pretko on a realization of fractons in whole doped antiferromagnets. And this work has been done at Columbia University. So let me get started. Okay. I'm going to try to be pedagogical as much as possible and give you a fast overview of everything I assume. So let me start by what I mean by fractons. So generically, this field of fractons started a few years ago, and in general, you see that there are two main properties in these systems. You have quasi-particles with restricted mobility. This mobility is usually restricted to a subdimensional space of the system. So for example, I could have a 3D system and then I get excitations that can only live in 2D or 1D. And then the other property is that there is a ground state degeneracy that is extensive in the system size. So that means as I increase the system size, my ground state degeneracy grows. And that is very unusual. This usually emerges in the context of some topological order. In 3 dimensions. The first models were Ha's code and then other models by Liang Fu and Vijay and Ha. But for the purpose of this talk, I'm not going to discuss the degeneracy. I'm not going to bother with that. I don't want to consider gauge symmetries or topological order necessarily, but I'm going to focus on subdimensional mobility constraints in some simple models and how they would arise in experiment. Just one sec to see if this. Should I continue? Okay. So, and how those arise in simple models. So it's worth to mention that the original models had 8-spin interactions. And so for the most part, there is some difficulty associated with realizing those models. Right now, I'm just going to consider simple spin models with 2-body interactions. So before I tell you how I do this, I'm going to just lay out the take-home message. I will convince you that fractal conservation laws emerge in whole doped antiferromagnets. And by that, I mean you will have quasi-particles reminiscent of fractons and dipoles. So a fracton will be one hole doped in the antiferromagnet and dressed by the magnetic background, and dipoles will be 2 holes bound together. And I will explain how the properties of the 1 hole and 2 hole states give us fractons and dipoles. I'll show that this behavior is robust. By that I mean that so long as you have the antiferromagnetic background, you will get that behavior. You can add small perturbations to that from the classical Ising limit, and the behavior will still be intact. This behavior is approximate in 2D and 3D antiferromagnets and simple antiferromagnets. It's exact in what I call the mixed dimensional 1D limit. And by playing with the lattice geometry, we can actually get even more constraints. So let's start by the details. So a fast overview of the physics of fractons I'm concerned by here has been fleshed out by Michael Pretko in a PRP in 2017. The main idea is that at low energies in some systems, you can get a continuum theory that's described by rank 2 symmetric tensor gauge theory. So basically, the vector potential is a rank 2 tensor. It's matrix valued and could be continuous or discrete. And that means that you have a constraint on the total charge of your system. It's just 2 derivatives of the electric field. And so from Gauss' law, we know that that means this is our first conservation law, that my charge is conserved. But it turns out that if I looked at this quantity, the dipole, it turns out to be also conserved. And so that was the main implication from that work that in these systems, I have severe restrictions on charge dynamics. I could have complete single charges completely isolated in the system, cannot move because that will violate the dipole conservation. However, if I have pairs of charges, they could move together so long as they have different charges because that will not violate dipole conservation. And that's exactly what we're going to be after right now. If we can get some simple systems that we're all aware of, that will have these properties. And this is interesting to have in real systems because there is new physics associated with dipole conservation. For example, in static thermodynamic quantities, you can show that because of dipole conservation, you can get at finite charge densities, phase separation, also referred to as emulsion physics. Essentially the particles want to cluster together. Or in dynamics, in absence of disorder, you can get slow thermalization. There's a new phenomenon related to this, referred to in the literature by Hilbert space fragmentation and discussed in many of these recent papers. So the physical setup for today's talk is hole-doped antiferromagnets. I'm going to study 1 and 2 hole states in those antiferromagnets. So here you see the spin up in blue, they have alternating antiferromagnetic order, and a hole is depicted by this circle. And I want to consider several situations. I'll consider the 2D limit. I'll consider something I call the mixed dimensional 1D limit. It's just a specific 1D model. I'll consider a honeycomb collinear model that's ongoing work. And in all these systems, I want to consider classical antiferromagnetic orders. That just means Ising interactions. And I will show that we can put spin exchange perturbatively and we don't lose much of what we find. So let's focus. The 3 parts of the talk will be 2D square antiferromagnet, the 1D model, the special 1D model, and the honeycomb collinear model. So let's focus on the 2D antiferromagnet. So the main idea is we want to look at 1 hole states first, and we want to see what happens there. So it turns out, and it's easy to see that if I take a single hole in this system, and then I allow it to move, so it's like a TJ model, where J is Ising, I can see that whenever the hole moves, for example, in this process, I get a spin that moves here, everything is nearest neighbor, but this spin is not happy because there are 3 frustrated bonds. This bond here, this bond to the left, and this bond to the bottom. So energetically, there's a cost associated with the motion of the hole in the antiferromagnet, unlike in the ferromagnetic case. And if you just keep doing this over and over in perturbation theory, you can show that the hole does not want to move at all, except for one particular 6-order process already fleshed out by Trugman in the context of high TC superconductivity, in which if the hole goes around a closed loop, it can actually move. So let's just go through this process because it will be important for what we discuss. So you apply the first motion, for example, the hole comes here. This is energetically unfavorable. The hole could go back and that means the hole will be localized, or the hole can start going around the loop. So for example, in the next step, it goes here, but then the blue spin has moved here. There are 2 unhappy bonds between this blue spin and this other blue spin. Okay, but then we can continue to go around the loop. So we come here. Now the red spin is unhappy. There's 1 bad unhappy bond here and 1 unhappy bond up there you don't see. But then we can keep going. Here, we move the hole 1 more step along that loop in real space. Again, there's a 3rd or a 4th spin that is unhappy with its neighbor here and the neighbor up there. But then if we move again and we come here, you start to see that I start to relieve the background, and I can go even 1 more step and everything is happy now. Right? So this high order process allows the hole to move to a next nearest neighbor site. But then you can even think about this as some constrained dynamics that is restricted to a single sublattice. This is courtesy or credit to Fiona and discussions where we flesh this out in more detail. So the point is, I can either think that parametrically up to before 6 orders in perturbation theory, my single holes do not move at all. So that's good, that's promising for Fracton-like quasiparticles. At 6 order in perturbation theory, I get this sublattice restricted dynamics, and that violates Fracton laws. But I need more than that. I need to see that I can get dipolar bound states. So let's look at 2 holes. Now it's very clear for 2 hole states that if I do the same kind of thing perturbatively, I move 1 hole, the red spin moves over there, and then, but it's unhappy. But then the second hole can hop and fix all the problems. So ready to leading order, I can get these 2 holes move together, and they conserve the relative separation between them. In fact, you can do this to arbitrary order in perturbation theory. And so long as perturbation theory works, you'll find that this is always true. There's a string that binds the 2 holes together and conserves the relative distance between the 2 holes. Each hole has a different spin quantum number, and that means we can associate the spin quantum number as a charge, and then that means single hole is a fracton, but the 2 hole bound state of 2 different charges is a dipole, and we get approximate fracton behavior in the 2D square antiferromagnet, and the details are in this paper in NPG Quantum Materials. But then we can even do better than this, and we can look at a specific 1D model. But before we look at a specific 1D model, one may ask, why don't you just look at your simple 1D chain? You know, where antiferromagnetism is not truly long-range ordered, it's power law, but still, we can try the same game. But if you do this in the 1D chain, you see that I move the hole here. This spin is unhappy. There's one bond that's frustrated. There's a domain wall, if you wish. But then afterwards, any subsequent hop has no problem at all, because all these spins can just get all reshuffled and retain the antiferromagnetic order. So it's not really a localization of the single charge. It's not really fractonic order. And this is just a manifestation of that we have spin charge separation in 1D. So from that, we just know that we need truly antiferromagnetic order. So what you could do is you can play some games. You can say, well, let's take a 2D antiferromagnet, but then restrict the hole to move only along the x direction, along one line. And that could be done in experiments by applying some small external field. And what you'll find is that the hole can move, but now there are no closed loops in real space. So the hole can go all along the line and come back because there's a string that attaches this to the origin. So you get complete localization of the single hole. That's a fracton, but then the 2 hole mechanism carries over as it used to be before. So I get a dipole, and now I have exact fracton behavior in this mixed dimensional model. Any questions at this point?
Why do you call it mixed dimensional 1D? It was 2D, no?
It is 2D, but the hole can only move in 1D. So the name is not courtesy to me. There's some other people, Demler and Fabian Grust. They call this type of model mixed dimensional. For me, it's simply the system is 2D, but the hole can only move in one direction.
But because of energetics, not because you force it to do.
No, you need to force it in this setup. You need to force it to move in one direction by an external field. So it will be energetics because of the external field. If we just go back to the full 2D case,
Yes.
there's this loop.
Yes.
So that allows the hole to move in the y direction. It moves in the x and the y because it moves to the next nearest neighbor.
Okay.
Right? So if I don't want to have that closed loop, I have to force the hole to move along a 1D line. So to force it, you need to apply some external field or some external perturbation that prevents it from moving in that 2D direction, just moves along one direction.
Okay.
Make sense?
Yes.
Okay. Okay, so I think I forgot to mention some other examples of other models that people have looked at. Perhaps maybe I go back to it later, but the point is this, I think at the time, was one of the few examples where You can just have a simple spin model, and you get that type of physics. Now we're looking at some other more complicated models. For example, the triangular lattice, the honeycomb model. Um, um, so right now, I just want to give you one particular example that's ongoing. This, what I call the honeycomb collinear antiferromagnet. So let me tell you what I mean by that. So I'm going to consider some honeycomb model in which I have some antiferromagnetic ordering, but the antiferromagnetic ordering is in the x direction only. So as you see, this is quite stable. You can do that. You just have all the spins in the x direction are antiferromagnetically ordered. However, the y direction is ferromagnetically ordered. And I believe there are some materials with these types of ordering where the ordering is not just uniform in all directions. Okay, and then we're going to consider the same kind of physics of single holes and two holes. So to explain what's going on here, the green arrow depicts the original position of the spin before I dope, and then when I dope, you know, a hole will be introduced, and then the hole could move by nearest neighbor hopping, and then when the spin moves, I'll depict it by red, so we know what's going on. Okay, so if we just consider single holes as before, I've convinced you, or I hope I convinced you, that the hole cannot move in the antiferromagnetic direction, because when it moves, the antiferromagnet is not happy. The spins start to have like bonds that are frustrated. So eventually, it has to come back, and so that will happen also here. Although in this case, the bonds that are unhappy are ferromagnetic bonds, but you know, this is very trivial to show. So as before, the single hole cannot move in the antiferromagnetic x direction. However, if we think about the y direction, the hole can come here, no problem, and the spin can come there, for example. So now you have, or let's just do this process that I've drawn. No, let's take this one. I think this would be better. The hole comes here. This spin comes there, so that's the red spin now. But there's no difference in energy between those two states. They are degenerate, so that's possible. But once this hole comes here, again, it cannot propagate further because there's nothing. It cannot jump here. That's far, and there is an antiferromagnetic line in the x direction, so it's trapped. So the single hole essentially becomes localized on the bond, on these bonds in the y direction, right? So again, single holes cannot move. So nothing very special about that. What's interesting is what happens for two hole states. So we can consider different configurations of two holes. Just to show you one particular example, let's focus on this, for example, but others also will have the same phenomenology more or less. So I can take two holes. I hop this hole, the spin comes here, but then I hop this hole here, that red spin now moves there, but it's unhappy because it wants to be antiferromagnetically aligned with its neighbors in the x direction. So the two holes don't want to move at all. And you can play this game over and over, but the point is the single holes, as before, they don't move, but the two holes don't move at all in the y direction. They move in the x direction, right? Because in the x direction, they just have to go through the antiferromagnetic background, and if they're nearest neighbors, that's fine. And we actually have numerical evidence. For the first model, it was more or less easier to do the perturbation theory to arbitrary orders on the square lattice. But on these honeycomb models, we wanted to do some numerics. So I hope you can see that here. But if you can see it, that's a 24 site cluster with exact diagonalization. There are two holes in the model. What you see here on the right is the Brillouin zone. These are the energies from we subtract the zero of energy, and you just have the symmetry label in the Brillouin zone with some symmetry label that has to do with the rotational symmetry. Let's ignore the rotational symmetry right now because it does not come into this discussion. But the point is, if I look, for example, at the y direction, which is the ferromagnetic direction, I should compare gamma and M1. So if I look at these states, gamma A1, and compare it to M1 A1, I can see if there's a dispersion in the y direction or there isn't. The same with gamma A2 and M1A2. It turns out that these states are exactly degenerate up to 5 digits, and that degeneracy increase, like the number of digits to which this is true, increases as you make the cluster increases. So it's pretty convincing that you have no dynamics essentially in the y direction. So from this, we conclude that the single holes, as before, are forming fractons, but pairs of holes, as before, move along the antiferromagnetic x direction, but they cannot move along the y direction. So that just means that we have even further constraints, and this is exact, further constraints on the dynamics of the dipole. They're restricted to a subdimensional manifold, which is a line. And I'm calling this just in line with the literature, dipolar linons. The term fractons was coined to mean that there's fractional dimensionality, and then linons means that they move along lines, and planons means they move along planes. And this work is with Sanyal and Vitek. It's currently in preparation. So I'm nearing the end of my talk. I don't have a very long talk. But let me just recap quickly the main ideas. I consider the square antiferromagnet. Everything is Ising interactions. I hope I convinced you that the single hole behavior is reminiscent of a fracton, but this is only approximate. This is true up to 5 orders in perturbation theory. After that, I get violations. 2 holes behave exactly as dipoles, but then I can get this behavior exactly in a mixed dimensional limit, which is this 1D model in a 2D background. I get single hole, again, is a fracton, and 2 holes are dipoles, and this is exact all orders in perturbation theory. And then I can take complex geometries with different kind of classical antiferromagnetic orders, and I can also find the same phenomenology, but I can even have more restrictions. For example, in this case, we found that the dipoles can only move along a line instead of moving along the full 2D. And I forgot to mention that's even more interesting. The parameters here, I don't know if the people on Zoom can see, but people here, I don't think they can see, but the parameters are actually not in the perturbative limit. They are far from the perturbative limit. So the value of T is around more than twice the value of J in these simulations, and we still find the same behavior. So now let me discuss, I'm sorry, yeah. Sorry, those values of what, sorry? Yeah, you mean what, how did you compute that? The framework is just to do exact diagonalization. This is just exact diagonalization with parallelizing over different symmetries of the Hamiltonian. Does that answer your question? So there's not, this is not an infinite system. This is 24 site cluster. So that's why you can't get full resolution in the Brillouin zone, right? Like you only have in this particular realization 2 sites, 2 k-states in the y direction. These are only k-states you have actually in the Brillouin zone if you do this, right? So it's not conclusive, but what's promising is that we did smaller clusters, not shown here, and we're running some bigger cluster, and we can see that along the y direction, the states are degenerate up to a certain number of digits, and that number of digits grows as you take a bigger cluster. So it's hard to think that this is not.
Does the ground state degeneracy grow with the size? Because otherwise, is Fracton, as you said also in the introduction, if only if there is this feature together with
yeah. So I don't, it depends on what you mean by degeneracy here. For example, obviously, these are degenerate states, right? This gamma and M.
Right.
So as you increase the system size, you'll get more key points. And, up to now, just 2 points. So we didn't see anything go bigger because we don't have full resolution. For the next iteration, we will see like the next system size, which is running, we will see if that's true for 3 points. But I don't think that's probably what you meant. You probably meant something in terms of topological degeneracy.
Well, yeah, I'm like in the X cube, in the standard
Yeah, I
fractonic codes.
I don't know, but I don't think it will be the
okay.
X cube. Like, we are not even designing these Hamiltonians and looking at these properties from that point of view, at least yet,
Okay.
right? Because again, the symmetries in our models, there's no at least apparent gauge structure. There might be, but we don't know as of now. So for now, it's just simply the realization of the conservation laws.
Okay. So you also then you have only this generalized Gauss law, but not the effective field theory, let's say gauge theory for this your models, right?
You will have the generalized Gauss's law
Yeah.
and the effective field theory of Pratko, but there are other the effective field theory of Pratko does not capture the topological, to the best of my knowledge.
Yeah, exactly.
So there are
Yeah.
more recent field theories by Slagle this year. I don't think we will have that, or at least we don't know if we have that. Like, it's unlikely that we have that.
You mean the foliated field theories?
Yes.
Okay.
The foliated field theory are, from my understanding, I think this is even, no, I think you're right. Yeah, I was just going to mention that there's the foliation started by just taking 2D toric codes or 2D gauge theories and just putting layers together to form a 3D Fracton theory. But I think Kevin managed to write a continuum theory somehow, but I don't know the details. But for those who's interested, this is a single author paper by Slagle in PRL this year.
Thank you. Thank you.
Okay. So this was my fast recap. So now the typical question one gets is, how robust is this to not having Ising interactions, having spin exchange? So at least, if we have spin exchange and Ising interactions of the same order, unlikely that this will survive. But the leading order in T over JZ, J perb, spin exchange does not do much. The way to see this is, just let's take this model in which the square lattice in which this behavior was parametric. And then if you move the hole by a single step, you get this configuration, which is which has 3 frustrated bonds. But the point is, there's no way here that nearest neighbor exchange can help you fix this problem, because all these bonds are aligned. You need something that where the two neighboring spins are anti-aligned. This could happen if you go one more step, right? So if J-perb is small, this will not affect that story, at least the leading order in T over JZ. So that also makes this a little interesting from the sense that it's not completely impossible that this will be parametrically stable. We think this could be readily realizable in materials. And then this will allow us to look at other things that could happen because of fractons, just because of the conservation laws, like the emotional physics I mentioned earlier, or the slow thermalization. We also discussed some of these details in the longer paper. So to summarize, I hope by this point you believe me that a hole in dressed by the magnetic background acts like a fracton, and two holes on neighboring sites form a bound state that is essentially a dipole, and that this fractal behavior is robust, not in a symmetry sense, at least for now, but more in the sense that it's stable to a small J perb, and it's exact in a mixed dimensional 1D limit, and allows us to get other interesting things. And then there are future directions would be actually to start to think about this from a symmetry principle, meaning I take some theory that has some specific order in the Landau-Ginzburg sense, and then I introduce defects in that theory. Is there some principle that I can develop that is general enough that will tell us if there's emergence of fracton conservation laws? We don't know. This is under investigation. And thank you for listening to me.
Thank you very much. Are there more questions? Just a moment.
So can you go back to the picture of the honeycomb?
Here?
The one previous, yeah. So if you've written the, the spin kind of orientation of the holes as it move through the lattice, if you'd say, have you tried kind of, for example, to simulate this using, for example, charge distribution or charge density distributions or electron density distribution, basically, or basically in the lab, in experiment? Like to
Well, I
notice
haven't,
this
I
behavior?
haven't tried that in the lab because I don't go to the lab. So maybe someone knows of some, we know of some materials that are related to this, but not one particular material. This is just an example. There are other more recently reported materials that have this behavior in layers. So from the point of view of experiment, I don't know. If you ask the same question about the square lattice, yeah, there are a lot of experiments on that and everything agrees, but the question is there some measurement that is so unique that can pinpoint this? That's a more difficult question, and we discuss it in the papers. Now, if you say I simulate the charge density, I don't know what you mean, compute the charge density numerically, is that what you mean?
Yes, yes. For example, within DFT or Hartree-Fock. Yeah.
But we don't need, like the only reason we would do that is if we want to get some information that goes beyond a 24-site cluster. You know what I mean? Because this is essentially exact up to system size, finite size effects, right? So I don't really see, for whatever we're interested in, you can simply, I view this as very convincing, especially that I can increase the system size, and I find that the degeneracy of different case states gets better.
I don't know. I cannot comment on that, but maybe, for example, which lattice are you kind of, did you calculate these for?
It's exactly the same lattice as that, but just 24 clusters, 24 sites.
Ah, okay, okay. So, yeah.
Yeah?
I thought you meant 24 atoms. So yeah.
No, 24 sites.
Okay. Thank you.
No problem.
A question I have is, maybe you can force this type of restricted mobility by boundary conditions.
Can you maybe elaborate a little bit more?
I mean, instead of taking periodic boundary condition, you put some sort of tension in the boundary, say,
Yeah.
and then that somehow propagate in the interior. For example, if you have an antiferromagnetic, you put, I don't know, on two sides the ferromagnetic boundary, and then they create some sort of tension that then propagates inside with a certain energetic.
Yeah. Okay. No, I haven't thought about that, but that sounds interesting. You're saying you can have a boundary condition that's not open boundary. You don't completely break translations, but
Yes.
you have some other boundary condition. You pick a phasor, for example, or something.
Some sort to introduce some sort of defect.
Yeah.
Or you think of periodic, but with some defect that somehow then propagates only creates some excitation,
Yeah.
which are a very strict mobility.
Yeah, I am not aware of anyone who has thought about that in the context of fractons, at least. So I'll be very interested. Do you know of specific examples?
No, just
Yeah.
came out of my mind, just
Yeah.
like this. Okay.
Yeah, it's possible, but I think I think it's possible, and I think what's interesting from this, other than that it's interesting for the people who are interested in antiferromagnets and so on, is if there's something more general that gives this. So, for example, there is a whole discussion by Pretko and collaborators about a duality between fractons and defects in disclination defects and defects in crystals. If you have just a crystal, you remove an atom, that there's a duality. And so there are many other systems. The realizations. I think I forgot to discuss this, but this slide here, there is this paper that was written prior to fractons, where essentially the phenomenology is there. If you take the thin torus limit of the quantum Hall effect, you will see dipolar symmetry is very clear there. Z2K theory of last week by Sergey Morris and collaborators. These are all different systems, but somehow energetically or because of symmetry, these conservation laws emerge. And so it would be interesting to understand if there's some more general reason behind that. As of now, I don't have that understanding, and the people I talk to don't have that understanding. So boundary conditions might be also possible. I just don't know. One has to try.
Okay, so yeah, you have a question.
So can one obtain some kind of dispersion relation for these dipoles?
Can you say that again? Sorry.
Can one get some dispersion relation for the dipoles?
Yeah. So I mean, you already, analytically, we already computed that. I didn't show you one equation here because I prefer not to, but you can go to the short paper or the long paper. But analytically, we computed the dispersion of that object, right? It will be cosine, 2t cosine t is the effective 2t star, which is the effective hopping of the pair, cosine k. Because what we found is to all orders of Hermitian theory, they always move together, right? So you can get all terms that conserve that. In the honeycomb case, you already see the dispersion numerically. So instead of, I focused on the talk on the y direction because I told you there's localization in the y direction. That means the dispersion is flat in the y direction. But if you look at gamma x0, k0, you look here, gamma is the blue on the very left, and then you can take k0, you already see that it's not the same, right? So there's some dispersion here, right? For the honeycomb model, it might be difficult to compute analytically to arbitrary order. I don't know yet. We will try that dispersion. But for the square lattice, I think we have a good understanding.
Is that a simple power? Or
Is it that simple?
power? A power like k squared?
For the square lattice, I think it's simple. Yeah, I think if you Taylor expand, yeah, it will be k squared.
Okay, thanks.
Well, if there are no more questions, we thank the speaker again.
Thank you.
Okay, thank you very much.